This code is horrible. It's really bad. You can see here it's unsafe. Here we use volatile memory accesses as a way of writing values to a variable. It's all trash. In this video, we're going to take this code from my other tutorial on doing embedded Rust and make it a little better using the idea of a peripheral access crate that will create ourselves using structures in Rust. Let's get into it. So if it isn't already incredibly obvious, this code is barely Rust. It is Rust in syntax and it does compile via the Rust compiler, but the code is almost entirely unsafe and uses things like write volatile and read volatile to put memory at a memory location. That's not incredibly rusty, and in this video I want to fix that. So to make the code a little more rusty, I'm going to create an interface to the addresses that we have written here. In the video I made before this, we actually wrote some bare metal code that ran on the Raspberry Pi, and we used it to turn a GPIO pin into an output and then use that pin to turn an LED on and off. We're going to create some interfaces that we can use as a programmer to make our code a little cleaner and more accessible to someone else that has to take that code on. The first thing we're going to do is we're going to create a byteless or a sizeless struct and call it GPIO, and then use the GPIO struct to implement some functions that will expose to the user that they can use to do things. So the first thing we have to do is turn pin 21 into an output using a function in the GPIO interface. So we'll create a public function called setOutput, and it'll take a parameter pin that is a type U32. And the whole point of this function, it returns nothing. It just does this functionality to turn a pin into an output. The way we do that is we consult the datasheet and we go and find the function selector register. If you didn't watch a previous video, not a big deal. I'll show you real quick. When we want to turn a pin on the Raspberry Pi to be an output, we have to write a particular value to a register called a function selection register. So for example, in this video, we're turning pin 21 to be an output. So to do that, we have to set bits 3 through 5 equal to 0, 0, 1 in the function select register 2. What the math turns into is if you want to set a pin 20 through 29, you use fcell2. If you want to use 10 through 19, you use fcell1. And if you want to use 0 through 9, you use fcell0. The math here is pin number divided by 10 gets you the register that you want to use. So we can actually do that operation to figure out, programmatically how to access the right register. So we'll say that let register equal a match statement on reg, where reg is going to be pin over 10. And the match statement will say if it's 0, GPIO fcell0. If it's 1, we'll do GPIO fcell1. And if it's 2, we'll do GPIO fcell2. And if it's something else, that's the default case there, we'll say panic, which is a macro, and we'll say something has gone terribly wrong. Okay, cool. So by doing this, we've actually created a match statement that produces the right address of the right register. These constants don't exist yet. We'll go up to the top of the screen real quick and fix these. So we want to actually create variables that represent the address of the function select register. We'll do that here by saying that 0, 1, and this will be at 4, this will be at 0. And all these addresses, in case you weren't aware, are coming from the Broadcom 2837 datasheet. Here are the addresses right there. And again, I talked about it in the previous video, but instead of 7E, it's 3F. Okay, so now that we've created the register that we want to read from, now we have to actually go through and read from it. So what we're going to do is create a variable called value. We'll let it be mutable. It's a type I32, and we'll set it equal to 0. Okay. Now what we can do is use our unsafe code and essentially steal this function here to read from that register. So we'll say that value is equal to read volatile. We're going to read from just register as a mute 32, and there's no value there. So what we have to do is we have to read the value out, to put our data in, and then write it back. Okay, so now that we've read the value out of the register that we've selected based off the pin number, we then have to actually make sure that our data is able to be put into there. The way we're going to do that is we have to what's called mask the value. So for example, if we wanted to set pin 21 to be an output, the value would have to be 001. But what if we read the value and it had 110 in there? By setting this one here for our output, we would actually turn it in to 111, which is no bueno. We don't want that, right? So we need to actually disable all of these first and then eventually turn on our value. Step 1, we have to create a mask. Step 2, we have to shift the mask to the right location. We then have to and in the not of the mask. I'll show you what that means here in a second. And then finally, we have to set our value. So the mask is going to be a value that is just 111, because again, we're dealing with 3 bits here. We'll make sure that it's set as a U32. I want this to also be a U32. Okay, so now that we have the mask set up, we need to shift it to the right location. So for example, I said that 21 divided by 10 gets you 2. How do we get to bit 3 from 21 in general? What it is it's the pin number, which is 21 mod 10 times 3. So say let pin num equal pin mod 10, and then mask is going to be shifted over by pin num times 3. So that'll put the ones we've created to the right position. And then now we want to actually take the value we've read out from the register and make sure that all of the zeros in that location are cleared. The way we'll do that is we'll say that val is equal to val and the not of the mask. And then what we can do is finally set our value. The way we'll do that is we'll say that val or equals 1 left shifted by pin number times 3. So this will actually put a 1 in bit 3's location. Awesome. So now that we've done that, we can use the same math here, the same code here to write volatile, and we're going to write value there. Awesome. So let's make sure this code all builds and I didn't make any grievous errors. I forgot a semicolon on line 33. Let's see what we got here. Yep. Boom. And then I don't want to read in val. I just want to write. Cannot assign twice to a mutable value. Oh, yeah, I need to make these all mutable. I'll say let mute mask and mute val. Okay, I think we're good. Okay, cool. A couple warnings, but we will make sure we go through and fix those. Yeah, so it's mad that all of these variables are not used, but there's no errors, so we're good. So what we can do now actually is pretty cool. We can actually use that code to replace our first line of unsafe code. How cool is that? So we can say GPIO set output pin 21. Boom. So at that point, after our code gets ran, GPIO is now set to be an output pin, and there's no unsafe code. So we can actually take the exact same methodology of, choose a register, read in a value, do some math on it, and put it back to create our next function, which is pretty awesome, right? So we'll say pub function set is going to take a pin. It'll be I32. Actually, no, it'll be a U32. I don't know why I keep doing that. There we go. Cool. So here we're going to do the same kind of operation to turn our pin on. And just like before, we have to write a value to a special register to make that operation happen. So the way we do that is we will write a bit to the bit location that represents the pin for output set register 0. So just like before, in our code, we have that commented out. We're going to take it and make it a global constant. So const GPIO, we'll call it set 0, is equal to the U32 of that address. We'll do the same exact thing for clear 0. We'll make it 28. Awesome. So for the set operation, it's the exact same thing. The bit position is going to be is equal to the pin. That's it. And then now we need to get the value. So let mute val and a U32 equal to 0. And we're going to read from our register where it's going to always be the GPIO set register. So now that we have val, we can shift in our bit or equals 1 left shifted by bit position. And then we can just write it back, same exact thing. And this will turn the pin on. And again, register is now GPIO set. Pretty awesome. And again, no return there. We're all good to go. If you can literally take this exact same functionality, call it clear, and then set the register to clear 0, not full clear, just clear. Let's make sure that our code compiles. Okay, a couple warnings, but no issue there. So we can actually do the same thing. And first of all, we can remove our entire unsafe block. That's pretty awesome. Now our code is safe in air quotes, even though it's really not. But here we can do, just like before, GPIO set 21, and then GPIO clear 21. Use of inline assembly. Oh, that's actually unsafe. Yeah. Copy and paste it real quick. Okay, it's mad about the mutability of the value file, but that's fine. And then one final thing we have to add is this attribute here. Previously, I had made a pretty hacky modification using global assembly to put the start function at the .text.start section in the code. We can actually use the link section notation here. This will actually put the code at the very beginning of the file so it gets built properly into our firmware. And then also one more thing that I did is I made a makefile. The makefile here just removes our target directory and then properly invokes rustc with our linker script as the linker script target so that it produces a clean and sane file for our project. So we'll go to my Raspberry Pi here. We'll make it, boom, a couple warnings, no issue. And then we'll actually object copy that like we did in the previous video to the kernel 7 image, and then I'll put that kernel 7 onto my SD card and we'll go from there. If you enjoyed this video, you should go watch this next video on getting Rust to run on the Raspberry Pi Pico, or this other video I think you'll also enjoy.